Hello there and welcome to module 4 of 18 labelled Wide Area Networks. So let's see what we're going to cover here, our objectives. Right, so effectively after completing this module you should be able to do the following. Distinguish between always on and on-demand WAN links. Distinguish between circuit switching and packet switching. Identify main media used by WANs. Then you should be able to recognise important leased line standards and also recognise important optical carrier standards and also PSTN based WAN links, so understand how those work, and PSTN and ISDN WAN links. You should also understand how the role of ADSL and cable modems in WANs. We'll also cover the basic operation of frame relay, ATM and MPLS. And finally, describe the principal features of common WAN standards and their associated cabling and connectors. So let's press on, and we'll talk a little bit about WANs and the different types. So most of the LANs that you would come across will be implementations of Ethernet and wireless LANs combined. By contrast, there's a much greater variety in the types of wide area networks available to you. This is in part a consequence of the different challenges presented by geography and terrain when making connections across large distances. It's also a reflection of the fact that these links are managed by different service providers as well. So we'll start by looking at several ways of classifying the different kinds of wide area networks. We'll distinguish between links that are always on and those that are dialed on demand. So we'll cover the difference between dedicated links, circuit switch links and packet switch links. And then we'll finish the section by looking at the different media types used by WAN links. What I forgot to mention also is we'll cover more of the important types of WAN implementations, from public switch telephone networks or PSTN with dial-up modems to frame relay. So there are a number of different ways of classifying WANs. First, we'll look at whether the link is permanent or created for the duration of the transmission. WAN links can be connections that are always on or dialed on demand. Ordinary telephone network or PSTN, which can be used to transfer data between remote sites, is an example of on-demand or dial-up network. Calls are typically charged by duration, although there may also be a line rental fee. This, in fairness, is a very rare technology and dying fast with the dawn of ADSL being so cheap and often provided free of charge when you order your telephone line. But dial-up internet is generally left for the unfortunate people that happen to live in remote locations where they are simply too far away from the DSLAM or the telephone exchange for them to get a reliable enough ADSL connection. Then always-on connections which do not require any dial-up. So this would effectively be ADSL, and these connections are always available unless there's a problem, of course. And these are known as always-on connections. There is typically a flat rate rental fee charged by the month, quarter or year. Leased lines are an example of this type of connection. So you have ADSL which goes down the copper telephone line, or leased line which is for the most part is dedicated fibre-optic cable running to your office. So I'll talk now about the different types of connections. So let's just move to the next slide. So we've got dedicated point-to-point, which is a serial connection supplied by a telecommunications service such as BT. Data travels directly from one end of the link to the other. There's no connection as such, it's typically an always on service. So just to give you an example, a diagram, let's go to here. So this is a typical example of a dedicated point-to-point connection, and although the line here shows connecting two routers together, at each one of the customer sites there is some extra equipment between the provider's line and the customer's router, and we'll learn more about this later in this module. So let's moving back, we'll go back to now circuit switch networks. So in a circuit switch network, a circuit or a fixed physical path is established when one system wishes to communicate with another on a network. Once established, that circuit is used for all traffic between the end systems until the call is terminated. And let me just show you. That's an example of circuit switch network. The next time the data needs to be transferred between the two systems, a new call is made and a different circuit may be established along that path. All the nodes inside the cloud. Every time a call is established, it could change the nodes that it uses to get to the other side, so to speak. This kind of connection is typical of dial-up networks. It is the mechanism used when making an ordinary telephone call over a public switch telephone network, or PSTN, and when using a PSTN to connect computers via modems. It is also used by ISDN, or Integrated Services Digital Network connections. You will learn more about networking using PSTN and ISDN later in this module. And the last type is packet switched. So in a packet switch network, the infrastructure provider accepts data packets from a sender and routes those packets through a network of packet switches before delivering them to the receiver. Packets from the same source to the same destination may take different routes through the network. I'll just show you the diagram. The packet switch functions like routers. The internet can be considered as a packet switch network. However, packet switch network providers will often offer a virtual circuit capability. To the end user, a virtual circuit appears as a dedicated circuit, similar to the one offered by a circuit switch network or leased line. A virtual circuit can be established whenever the source calls a destination and is referred to as a switched virtual circuit, or an SVC. A virtual circuit that is permanently established between the source and the destination is called a permanent virtual circuit, or PVC. This mechanism can be used to provide dial-up, SVC, and always-on, PVC, connections. Frame relay is an example of this kind of network infrastructure, and you'll learn more about frame relay later in this module. So let's move to connection media. Sorry about this, I am flicking backwards and forwards between screens. So as in the case of LANs and WANs, the links use copper wire and fibre-optic cabling, as well as wireless links. Although the structure of the cables, the signalling methods and the speeds will often be different. So copper connections, let's talk about those first. There are a number of different copper-based technologies used to provide WAN links. These include PSTN, ISDN, leased line, DSL and cable, which are covered later in this module as well. Many high-speed copper connections, such as leased line and primary rate ISDN, or PRI, consist of links with data rates in multiples of 64 kilobits per second. This basic channel is referred to as a DSO, or Digital Signal Zero. In the US, 24 of these channels are bundled together in a DS1 channel, carried over a T1 connection. This provides a capacity of 1536 megabits per second. However, 8 kilobits per second are needed for synchronization, which is used to separate the channels. So, the actual speed of a T1 connection is 1.544 megabits per second. It is also possible to bundle 28 DS1 channels in a DS3 channel, which is carried over a T3 connection. The T designation was originally assigned by the old US telecoms company Bell. In Japan, the same bundle is referred to as a J1 connection. In Europe and most of the rest of the world, the basic bundle called E1 consists of 32 DSO channels with a total speed of up to 2 megabits per second. Only 31 of the channels are available for data transfer, the other being used for synchronization. There are also larger bundles, some of the most important, which are shown here. Bundles of DSO channels smaller than T1, E1 or J1 are available, and they're referred to as fractional T1, E1 and J1 respectively. Although the T, E and J designations applied to copper cable originally, the T3, E3 and J3 bundles are generally provided over fibre-optic cable. We'll talk now about fibre-optic connections. So I'll just move on. So there are other standards for WAN fibre-optic connections. In the US there is SONET, or Synchronous Optical Network. This defines connections in terms of optical carrier channels. The basic channel is Optical Carrier Level 1, or OC1, which provides a speed of 51.84 megabits per second. Its international equivalent is SDH, or Synchronous Digital Hierarchy, which defines connections in terms of STM, or Synchronous Transport Modules, levels, of which the basic level is STM0. Some of the more important OC and STM levels are shown on the screen right now. So the main use of SONET or SDH is to multiplex different kinds of traffic over fast, long distance fibre optic links. SONET or SDH define physical connections and signalling methods at OSI layer 1 and frames at OSI layer 2. These frames are able to carry other PDUs such as Ethernet frames, IP packets and ATM cells, which we will describe later in this module. Voice traffic can also be carried. There are two main topologies, point-to-point and ring. There are variants of the ring topology, but they all include a dual ring with self-healing ability, as shown on the screen right now. So let's talk about the passive optical network, or PON. Delivering point-to-point optical connections to a number of locations can be expensive. One alternative is to use point-to-multipoint architecture, as shown on the screen now. An optical line terminal, or OLT, connects to a service provider's passive optical network to the rest of its network. A single fibre from the OLT passes through a splitter. This is an unpowered device, hence the term passive, which simply splits an optical signal and sends it to a number of downstream optical network units, or ONUs, at customer sites. The ONUs convert the optical signal into the electrical format used at the end site. An ONU is also known as an optical network terminal if it serves a single customer instead of serving a multi-tenancy site. Downstream signals are broadcast to the ONUs. Upstream signals are multiplexed, usually by a form of TDM, or time division multiplexing, controlled by the OLT. Wireless links, such as microwave links and satellite links, have been used for decades for voice, video and data connections. More recently, cellular phone networks have also been used to transfer data. Point-to-point wireless connections can be made between buildings, often using microwave frequency signals in the range from 1 GHz to 40 GHz, as shown on the screen. These kinds of links require a line of sight between the endpoints. The microwaves can be focused by parabolic dishes and sent as direct beams. This means that the received signal is much stronger than it would be if it would broadcast in all directions by an omnidirectional aerial. the speeds are comparable to WLAN speeds. Obviously, the point-to-point link is great, but it's very susceptible to weather conditions, wind, rain, snow and whatnot. So that has to be considered when thinking about a solution. So other WAN links are, as you can see on the screen, a satellite. So satellite communications can also be used to provide WAN links to locations where it would be harder to deliver cabled connections, for example ships at sea. Providers can offer private WAN services over satellite links, sometimes referred to as VSAT. However, speeds tend to be low, in order of a few megabits per second. More seriously, there are delays in relaying data via satellite, making satellite communication less suitable for applications such as voice communications, which require low latency. Then we have cellular. Cellular phone networks were developed to carry voice traffic to and from mobile cellular phones. As mobile phone technology has advanced, these networks have also been adapted to carry data. The HSPA, Evolved High-Speed Packet Access standards, offer download speeds of up to 168 megabits per second and upload speeds of 22 megabits per second. This is used by 3G data services over mobile devices. Most modern mobile phones are smartphones with computer functionality in addition to voice functionality. They are able to use network data directly, for example browsing the web. They can also be attached to a PC, typically a laptop, to provide the PC with network access, a process known as tethering. A PC does not have to use a mobile phone to gain access to wireless broadband networks. The broadband connectivity can be provided by a USB stick or a built-in device, as is the case with many tablet devices. The newer LTE, or Long-Term Evolution standard, allows wireless broadband data transfers up to mobile phone devices with download speeds of up to 300 megabits per second and upload speeds of up to 75 megabits per second. Quite staggering speeds for mobile phones. This is the basis of 4G, or fourth generation mobile data services. You should be aware that the quoted speeds are theoretical limits for the technologies. Actual speeds are likely to be less where there is a signal degradation or contention, i.e. many users attempting to access the network simultaneously. Finally, we'll talk about WiMAX. The IEEE 802.16 WiMAX standard provides wireless broadband access with a signal radius of approximately 50 kilometers, allowing the creation of wireless MANs, which stands for Metropolitan Area Networks. The 2011 revision of the standard supports theoretical speeds of up to 1 gigabits per second. Again, actual speeds are likely to be less. So let's talk about WAN layer 2 protocols. Okay. The frame types used by the data link layers of WAN protocols are often different from the Ethernet frame type we saw earlier, particularly in the fact that they do not need to carry MAC addresses in their headers, as the links are point-to-point rather than broadcast, and so there is no need to specify a source or destination address. The main WAN data link protocols are HDLC, Frame Relay and PPP. They are defined by open standards. PPP has a number of advantages over HDLC, particularly its ability to support multiple packet types and to implement authentication and other security features. We will cover more about HDLC and PPP in Module 12, which is labelled Configuring an Access Router, and we'll learn about Frame Relay in Module 13. Although most Layer 2 protocols do not require equivalent of a MAC address, Frame Relay frames carry information about the Data Link Connection Identifier, or DELCI, which allows them to specify which virtual circuit should be used. This is particularly important as Frame Relay supports point-to-multipoint links. Another Layer 2 protocol, known as SLIP, or Serial Line Internet Protocol, is only capable of handling IP packets and has poor security. It is also slower than PPP, which has largely replaced it. So we'll talk now about PSTN. Let's have a look. This is a slide for it. PSTN, also known as Plain Old Telephone System, or POTS, which uses ordinary voice grey telephone lines, was among the most common means of providing WAN connectivity. This was particularly true for home users connecting their PCs to the internet via an internet service provider, or ISP, and for mobile workers connecting mobile computers to the office LAN. Data transfer rates are generally slow, typically around 33 to 56 kilobits per second. This technology has largely been superseded by ADSL and cable modem connections. Fast data transfer over voice-grade telephone lines is not possible, as the bandwidth of these lines is limited to the 300 to 3000 Hz range. This is adequate for reproducing conversations, and limiting bandwidth of each conversation allows more of them to be multiplexed over the trunk connections between exchanges. In order to transfer digital data across a PSTN system, it is necessary to use an analog, voice-like signal capable of propagating without distortion along the line. This carrier signal is modulated to encode it with the digital data from the sender. At the other end, the signal must be demodulated to extract the digital data. This process is carried out at each end by a modem, as shown on the screen. PSTN links offer on-demand connections over circuit-switched networks. The modem used for PSTN connections are asynchronous, i.e. they do not exchange a timing signal with a digital data source, usually a computer or a router. The modem needs to detect each bit sent by the computer. To do this, it must sample the digital data from the computer at exactly the same rate at which the computer generates it. The lack of a common clock at either end means that the modem and computer could become out of sync with each other when transferring long streams of data, resulting in bits being missed or counted twice. Consequently, asynchronous modems only handle very short bursts of data from the computer, typically a byte at a time. This prevents the clock from diverging too much during the transmission. It also has the effect of slowing down communications. The lack of extra timing circuitry makes asynchronous modems cheaper, but results in slower transmission rates. You can see an example of asynchronous modems on the screen right now. There you have it. The modem is referred to as the DCE, or Data Circuit Terminating Equipment. The end device, for example computer or router, is referred to as the DTE, the Data Terminal Equipment. Asynchronous modems typically use a cable with two DB9 connectors, one male and the other female. The female end, shown on the top right hand corner of this slide, connects to the PC, while the male end connects to the modem. The PC connector can also be a USB connector, as shown on the slide at the bottom middle, obviously your standard USB connection. The connection between the modem and the PSTN usually has an RJ11 connector, which is on the bottom right hand corner of the screen, and what you see now will connect to the modem end, and the local PSTN connectors at the other end. It's a standard, basically a standard type telephone socket connector. The RS232 standard is the most widely used standard defining the interface between the computer and the modem. The term RS232 refers to the family of recommended standards developed by the Electronic Industries Alliance. Today, the official name for the base standard is EIA 232, but RS232 is commonly used. RS232 defines a number of circuits which are used to send data to and from the modem, and to control the way that the data is sent. Asynchronous modems only use a subset of these as they do not use clocking signals, as explained earlier. The pinouts for a female DB9 connector are shown on the next slide. Here we have it. The pins are numbered sequentially from the left. When looking at the connector, pin 1 is the first pin in the row of 5. Pin 6 is the first pin in the row of 4. Pins 2 and 3 are used to receive and send data. Pins 5 provides the ground relative to which the voltages on the other pins are measured. The other pins provide information for controlling the data flow between the DCE and the DTE, a process sometimes known as handshaking. It is possible to connect two DTEs together via a serial link without using a modem. This is often convenient for transferring files between PCs which are not attached to a LAN. You can do this using a null modem cable. The simplest form of this consists of two female DB9 connectors with the transmit pin, pin 3, of each connected to the receive pin, pin 2, of the other, and the two signal ground pins, pin 5, connected to each other. It is the serial equivalent of an Ethernet crossover cable. Leased lines are permanent data quality links supplied by telecommunications companies, especially for the purpose of supporting digital data transfer. Leased lines can be supplied with speeds in multiples of 64 kilobits per second, with capacities of up to millions of bytes per second. Apart from being always on, leased lines also have the benefit of offering uncontended access, i.e. no one else shares your bandwidth. Companies offer various levels of leased line connectivity. The most common are the T1 and T3 leased lines in the US and the corresponding European equivalents of E1 and E3. Because of the higher data rates supported by leased lines, they are generally used in conjunction with synchronous modems. These modems ensure that DTE and DCE stay synchronized, enabling longer frames to be sent. They do this by transmitting clock information to the DTE. The extra circuitry required to do this makes them more expensive than asynchronous modems. A CSU, DSU, or Channel Service Unit / Data Service Unit, is required at each end of a leased line. It connects the leased line to a device on the local network, usually a router, as you can see on the screen. It consists of the following components. CSU. This functions as a protection and diagnostic device for a leased line. DSU. This connects a terminal to a leased line, controls the line and performs a digital to analog conversion, i.e. it is the synchronous modem, or DCE. The CSU and DSU are often supplied together as a single unit. The wiring for a leased line is often terminated before the CSU and DSU at a place called the demarc, or demarcation point. So when, for example, BT come in to install your leased line, they will declare the demarcation point at which it is up to that point, the demarcation point, where they would be responsible. And so this marks the extent of the service provider's responsibility for the service. The cabling between the demarc and the DSU-CSU is often called the extended demarc. The CSU-DSU belongs to the service provider and is often referred to as the customer premises equipment. The demarc may simply be an RJ45 jack. However, the service provider may also provide a smart jack, which can be looped back for testing the circuit to the demarc point. Cabling and connectors. Leased line connections can use the EIA232 protocol, but in this case they must use the full 25-pin connector shown on the slide at the moment. This supports the extra circuits needed for the timing signal, which is used to synchronize the DTE and DCE. Two other EIA protocols are also used with leased lines, EIA449 and EIA530, which are enhancements of the EIA232 protocol. Each of these also uses a DB25 connector, like the one shown on screen. Another widely used leased line cabling standard is X21, which uses a DB15 connector, similar to the one used in an Ethernet AUI. You will learn more about X21 cables in Module 7, as these cables are used in a number of the practical labs. The X21 standard is defined by the ITU-T, or the International Telecommunications Union Telecommunications Standardization Sector. The ITU-T replaced the former CCITT. In the US, the V.35 standard is also widespread. This uses a 34-pin connector, like so, as you can see at the bottom, with thicker spring-loaded pins. The V.35 standard is also defined by the ITU-T. Let's talk briefly about ISDN. Telecom providers offer two ISDN services: a basic rate interface, or BRI, service, and a primary rate interface, or PRI service. They are on-demand or dial-up services over circuit-switched networks, capable of carrying both voice and data traffic. The BRI service is delivered over data quality phone lines. It provides two channels for user data and one channel for control functions such as call setup. The channels which carry the user data are known as the bearer channels, or B channels. And the channel that carries the control information, such as data signals, is known as the data channel, or D channel. The capacities of the channels are shown on screen. The service offers a capacity of 128 kilobits per second over the two B channels, which can be aggregated. If the D channel is inactive, it can also carry user data, giving potential maximum of 144 kilobits per second, i.e. when you bond them all together. Basic rate ISDN was typically used to connect SOHO small office home office networks to corporate intranets or to the internet via an ISP. It has been largely superseded by ADSL and cable modem connections, which offer faster, always-on access to voice, video and data networks. Primary rate ISDN is designed to provide voice and data services to businesses and other organisations. There are two variants, one used mainly in North America and Japan, and the other used in Europe and elsewhere. So what you see on the screen at the moment is North America and Japan. If you note the speeds in the B channels, D channels, there's also synchronization signals. And then we've got the PRI ISDN channels in Europe. Note the cabling and connection methods are similar to those used for leased line connections. So we'll now talk about DSL. So digital subscriber line services provide high-speed access to local exchanges for voice and data over data quality phone lines. There are two main types of DSL: ADSL, asymmetric DSL, and SDSL, symmetric DSL, referred to collectively as XDSL or simply DSL. The first is the cheaper and more popular. It provides higher download speeds than upload speeds, ideal for users who mainly use the connection for downloading web pages. SDSL uses two channels of the same speed and is used predominantly by small organisations. A DSL line can carry ordinary unmodulated voice traffic as well as data traffic using an inaudible high frequency modulated signal from a DSL modem. The data is carried in two separate channels, a downstream and an upstream channel. Let's look at the diagram. As I said, they're carried over two separate channels, a downstream and an upstream channel over data quality phone lines. As most DSL connections are ADSL connections, we shall refer to ADSL except when speaking explicitly about other form of DSL. At the local exchange or central office, the voice traffic is split from the data traffic, as shown on screen. This is done by a DSLAM, or Digital Subscriber Line Access Multiplexer. The voice traffic is routed to the PSTN. the data is sent to the ISP's router. The ISP may be the PSTN provider itself or a separate organisation whose routers are hosted or co-located by the PSTN provider at the CO. The link between the DSLAM and the router carries the traffic of a number of different subscribers who contend for the bandwidth of that link. The term contention ratio refers to how many subscribers at any one time may be trying to use the link between the DSLAM and the router. A contention of 50-1 means that here might be up to 50 users trying to use the link at any one time. At the subscriber end, the low frequency voice component of the signal is split from the higher frequencies carrying the data. An ADSL modem or ADSL enabled router is connected to the ADSL data socket, while the telephone is connected directly to the ADSL phone socket. ADSL routers often have 4 Ethernet ports for connecting to the subscriber's equipment. The ADSL router will normally have its IP address assigned dynamically by the ISP. And the ADSL router may in turn dynamically configure the IP addresses of the subscriber's PCs. That's generally what usually happens anyway. There are a number of ADSL Layer 1 standards defining encoding methods, speeds and distances from the subscriber to the local CO. Speeds varying from 144 kilobits per second to just over 50 megabits per second, which would be for a fibre-optical connection. Distances vary from over 1.5 kilometers to about 9 kilometers. At layer 2, ADSL uses PPPoE, which is PPP over ATM protocol, or the PPPoE, which is PPP over Ethernet protocol. You have already seen that PPP supports authentication, which is a useful feature for infrastructure providers. Many of these use for their infrastructures Gigabit Ethernet or Asynchronous Transfer Mode, or ATM, which are described later in this module. ADSL is widely used for SOHO connections to the internet. ADSL has advantages over analog modems and ISDN connections, be it the speeds are generally higher and the data connection is always on, i.e. no dialing or call setup is required for data connections. On the negative side, ADSL is not available in remote locations owing to the distance restrictions. Also, whilst the speed on the local loop to the exchange is unaffected by the presence of other subscribers, there will be a contention for the link between the DSLAM and the ISP's router, which can reduce data transfer rates at busy times. ADSL provides an always-on service over a packet switch network infrastructure, something to remember. There are a number of ADSL standards offering various speeds. One of the fastest currently is VDSL, or Very High Bitrate DSL, which has speeds of approximately 100 megabits per second in each direction, although these can only be achieved over a short distance of the order of 300 meters. Broadband cable. Cable TV providers use broadband technology to deliver multiple TV channels to the subscribers. If they provide data access as well, 2 channels are used for data. One for downstream data from the cable provider to the subscribers, and one for upstream data from the subscribers to the provider. Downstream speeds can be up to 40 megabits per second. Upstream speeds can be between 320 kilobits per second and 10 megabits per second. The latest Virgin Media services can offer up to 150 megabits per second downstream, which is blistering the speed for the home. All the subscribers are connected to the distribution cable by drop cables as shown on the screen. This means that all subscribers can potentially see the upstream and downstream data rather like stations connected to an Ethernet cable. Subscribers with sniffer software could effectively eavesdrop on communications, which needs to be encrypted to prevent this. Cable modem communications use MCNS, or multi-cable network systems, MAC addresses to identify which stations are to receive data and which have sent it. Broadband cable provides an always-on service over a packet switch network infrastructure too. One of the problems associated with cable modems is that as more subscribers are added, there is more contention. This causes particular problems for the upstream data because the lengths of the distribution cables means that it cannot be efficient to use a simple collision detection mechanism as used by Ethernet. Collisions on cable are minimized by the use of TDMA, or Time Division Multiple Access Protocol, which assigns a time slot for transmission to each station. Frame relay is another packet switch service offered by some telecommunication providers. It is capable of providing always-on PVCs between locations, as well as on-demand switched virtual circuits, SVCs. On the screen, as you see, an organisation has a router at each of its 3 offices. Each router is connected to a local frame relay switch in the telecommunication provider's frame relay network. The frame relay provider has set up 2 virtual circuits for the organisation. One connects router B to router A at the head office, and the other connects router C to router A. Although router A has 2 virtual circuits, it only needs one serial connection to the local frame relay switch. This saves on the cost of connections and of interfaces on router A. In the case of a head office connected to hundreds of branches, the savings can be very significant indeed. When router A sends frames to its local frame relay switch, it needs to select which virtual circuit should be used. Each virtual circuit at router A is identified by a DELC, or a Data Link Connection Identifier, which is a number supplied by the frame relay provider. You should note that router B may have a different DELC for its virtual circuit at A. This does not matter as long as each virtual circuit has a different DELC. The DELC acts as a frame address, telling the frame relay switch which virtual circuit to use to forward the frame to its destination. In this respect, it performs a similar function to a MAC address. Asynchronous transfer mode technology is based on efforts to develop broadband integrated services digital network, or BISDN, for the high-speed transfer of voice, video and data through public networks. ATM is capable of transferring voice, video and data through private networks and across public networks. ATM uses very large scalable integration, or VLSI, technology to segment data at high speeds into units called cells. Each cell consists of 5 bytes of header information and 48 bytes of payload data, as shown on screen. Cells cross ATM networks by passing through devices known as ATM switches, which analyse information in the header in order to switch the cell to the output interface that connects the switch to the next switch in the cell's route to its destination. By the very fact that the cells are small makes it easier to guarantee time slots to services that demand it, for example video applications. As the cells are of the same size, they can be processed in parallel by the ATM switching elements. This allows the construction of very large switch arrays of identical elements using VLSI technology. ATM is a cell switching and multiplexing technology that combines the benefits of circuit switching with those of packet switching. As network infrastructures become faster and latencies have diminished, the advantage of breaking packets up into small cells to guarantee quality of service has been increasingly undermined by the overhead, fragmentation and reassembly. One of the problems with ATM and frame relay is that there are layer 2 technologies and that their techniques cannot be exploited at layer 3. MPLS, however, is an emerging approach which incorporates some of the features of ATM but is also capable with IP at layer 3. It does this by adding an MPS label to the IP packet. This allows the packet to be routed by IP through those parts of the network without MPLS switches. However, when a packet enters an MPLS network, it has an MPLS header attached to it which contains a label. This label has the information necessary to route the packet through the MPLS network. On leaving the MPLS network, the MPLS header, including the label, is removed and the IP packet can continue to be routed through the IP network as normal. This makes it much easier to incorporate MPLS networks within IP networks and route seamlessly across both. Because MPLS header is between the frame and the IP headers, it is sometimes referred to as it operating at layer 2.5. You will learn more about MPLS in Module 9. Although Ethernet is considered a LAN protocol, the advent of 10 gigabit Ethernet cable of being carried by fibre optic cables over long distances has allowed infrastructure providers to offer virtual private LAN services, or VPLSs. This allows VLANs to be set up comprising multiple sites separated by large distances. It can also be run over MPLS when it is known as Ethernet over MPLS or EO MPLS. Other Ethernet WAN services include Metropolitan Ethernet or Metro E. So that completes Module 4. Just to review, having completed this module, you should be able to distinguish between always on and always on demand WAN links, distinguish between circuit switching and packet switching, identify the main media used by WAN links, recognize important leased line standards, recognize important optical carrier standards, describe PSTN based WAN links, also ISDN based WAN links, and should also know and describe the role of ADSL and cable modems in WANs, also the basic operation of frame relay. We've touched on ATM and MPLS, and you should also be able to describe the principal features of common WAN standards and their associated cabling and connections. Thank you for listening to my Module 4. Next module is Module 5, and its subject is networking with TCP/IP. Very, very interesting, and I hope you come back and watch. Thanks for watching. Bye bye.